Hello, in this problem we'll be looking at flow continuity and an energy balance once again. Alright, so we have a figure above and it's of a piping system with constant elevation, so that means there are no changes in potential energy. And we're given some of the values for the cross-sectional areas and the linear velocities through the piping system, and we're told that water flows through this pipe and it forks into pipe 2 and pipe 3, and we're also given another useful piece of information that the volumetric flow rate of the fluid in pipe 2 and pipe 3 is identical. Alright, and we have three different things we want to calculate. First, the linear velocity of the fluid in pipe 1, U1, and then the linear velocity of the fluid in pipe 2, and we're also given some information about the kinetic energy, so we want U2. And then lastly, part C, we want the cross-sectional area of pipe 2, A2. Alright, so from flow continuity, we know that the initial volumetric flow rate has to equal the final volumetric flow rate. But we don't just have one pipe. We have a pipe that is splitting into two separate streams. So we can rewrite this as follows. And for any volumetric flow rate, you can split it up into its components. The volumetric flow rate will be equal to the linear velocity times the cross-sectional area. So let's look at that for pipe 3. And fortunately, we were given both of these pieces of information, so we can get that the volumetric flow rate through pipe 3 is 3 times 1.5, or 4.50 meters cubed per second. And we're also told that the volumetric flow rate through pipe 2 and 3 are equal. So that means that this must also be 4.50 meters cubed per second. Okay. And from above, we have that the initial volumetric flow rate is going to be the sum of the second and third volumetric flow rates. Okay, so taking this volumetric flow rate and this volumetric flow rate, summing them, we get that our initial volumetric flow rate is 9.00 meters cubed per second. And we're also given the cross-sectional area as 9.00 meters squared. And just as we did before, we can use the relationship that V1 equals U1 times A1, or the linear velocity is 9 divided by 9. So we get the answer to part A, that the linear velocity of the fluid through pipe 1 is 1 meter per second. Alright, so moving on to part B, we want the linear velocity of the fluid going through pipe 2. And if we try to use the relationship V2 equals U2A2, we actually don't have enough information to solve for U2. We have the volumetric flow rate, which we solve for as 4.50 meters cubed per second, but we don't have the cross-sectional area, so we can't get the linear velocity. But we are provided some other useful information. We're told that the kinetic energy increases at a rate of 56,812.5 watts across the fork. Alright, so what can we take away from this? So, looking at our initial kinetic energy and our final kinetic energy, they tell us that we increase, that the rate of the kinetic energy increases 56,812.5 watts. Okay, so I think we have enough information to get our initial kinetic energy. That if we write that out, that's just 1/2 mass flow rate times the velocity squared. And we know this is water, so we can get the mass flow rate from the volumetric flow rate. Alright, so we have the volumetric flow rate through pipe 1 as 9 meters cubed per second. So multiplying by the density, 1,000 kilograms per meter cubed, we have that the mass flow rate is 9,000 kilograms per second. And similarly, doing that with pipe 2 and pipe 3, we get that the mass flow rate is 4,500 kilograms per second. Okay, so for our initial kinetic energy, we have 1/2 times 9,000 times 1 squared, and that's just 4,500 watts. Okay, and we're told the rate that the kinetic energy is increasing, so we can get our final kinetic energy by adding the increase to our initial, and we'll get 61,312.5 watts. Alright, so if we have the final kinetic energy rate right here, we can break that down into the components in pipe 2 and pipe 3. Okay, and for each of these kinetic energies, that's just going to be 1/2 times the mass flow rate times the velocity squared for their respective streams. Okay, and I think we have all the values we need to solve. We have our second mass flow rate, our third mass flow rate, and the third linear velocity. So the only unknown is the second linear velocity here. So if you plug in the appropriate values and solve for U2, you'll get 5 meters per second. And this is part B. And our last part, part C, they want to know what the cross-sectional area of pipe 2 is. And we can use the relationship V2 equals U2 times A2. And now that we have both the volumetric flow rate and the linear velocity, we can get the cross-sectional area. And that's just going to be 4.5 meters cubed per second over 5 meters per second. And that gives us 0.9. So our final answer, part C, is that the cross-sectional area is 0.900 meters squared. Okay, as always, thanks for watching. I hope you found this helpful.